بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. In this series, we will try to cover some questions as the coverage suggested by the ESE for term 2 this year. This series will be in more than one part. At the end of each video, you will find link for the other videos, inshallah. Let's start. The first outcome is about identifying the electron volt as an energy unit. The electron volt is the energy gained by electron or proton by electron or proton when accelerated within 1 volt. So as we discussed in term 1, delta K equals minus delta U, which is Q delta V. Now, if the charge is electron, I mean 1 electron, and the potential difference is 1 volt, then the answer would be 1.6 times 10 to the minus 19 coulomb times 1 volt. It is 1.6 times 10 to the minus 19 joule. This amount is named as electron volt. So every electron volt is 1.6 times 10 to the minus 19 joule. Now, what is the joule? Joule, it is the unit of energy, and it is equivalent to newtons times meter, as the work said. Newton is kilogram meter per second square. Since the force is m times a, Newton is equivalent to kilogram for the mass. For the acceleration, it is meter per second square. Then go back to the joule. Joule is 1 Newton. This is the Newton multiplied by m. M, it is a meter. Then the joule is kilogram meter squared per second squared, or kilogram meter squared second to the minus 2. So this is the unit of joule in the SI units, kilogram meter squared per second squared. So the answer should be C. And the electron volt is a unit for measuring the energy, and it is equal to 1.6 times 10 to the minus 19 joule. Now let's go to the second outcome. This outcome is about relating the work done by the gravitational force and the gravitational potential energy for an object lifted from rest to a height of h. The thing is, the work done by the gravity is the force by the gravity times the distance d, then cosine theta. Now, Fg, it is the weight, so it is mg. D, we usually name the distance by lifting or lowering as h, the height, cosine theta. Now, the most important thing is cosine theta. Now, if the object is down, then you lift it up. So the distance should be positive, while the force of the gravity is downward. So the angle between the force and the distance or the displacement is 180. And we know that cosine 180 is -1. Then the work done by the gravity for lifting an object is minus mgh. And if you want to lower some object from point up to down here, so the distance is downward, it is negative, and the force of gravity, it is downward as well. So the angle between D and F is 0. Cosine 0 is 1. So the work done by the gravity is positive mgh. At last, if you are lifting an object and then you are going to the right or left, this is the distance. The gravity is downward, so the angle is 90. And we know cosine 90 is 0. So the work done by the gravity, in this case, is 0. This is the full picture for the work done by the gravity. What about the relation between work done by the gravity and the potential energy? We know that the potential energy, U, equals mgh. Compare it with the work done by the gravity in these two cases. Even in the third one. If you want to compare them, you just want to put the work done by the gravity is equal to the minus of the change in the potential energy, which is minus mg delta h. So if delta h while going up, then it would be positive. Positive times negative, it is negative, which is the first one here. If the object is going down, so delta h would be negative. This is down. That one is up. Negative times negative, it is positive. So this situation. At last, if you are going to left or right, delta h would be 0. Then you will get this situation. So the work done by the gravity always equal minus delta u, minus mg delta h, and delta h is h final minus h initial. And we have the sign of delta h will decide what is the work, positive or negative or even 0. Okay? If the object is going down, delta h would be negative. If the object is going up, delta h would be positive. And if it in the horizontal or parallel to the horizontal, delta h would be 0. These are the three cases for such a problem. Now let's go to outcome number 3. In this outcome, we will discuss the conservation of mechanical energy in any situation. And really, this is a very interesting example. First, let us discuss what is the conservation of mechanical energy. We know that the mechanical energy is the kinetic energy plus the potential energy. Now, if there is no forces applied or no resultant force applied on the system, then the kinetic energy plus the potential energy, which is the mechanical energy, should be conserved. That means the initial mechanical energy equals the final mechanical energy. Or we can put it like this: delta mechanical energy equals 0. Or we can put it like this: kinetic energy final plus potential energy final equals the initial potential kinetic energy and the initial potential energy. If we make shifting of k and u, we'll get that delta k equals minus delta u. All of these expressions are conservation of mechanical energy. Now, let's go back to this question. A pendulum swings in a vertical plane. At the bottom of the swing, the kinetic energy is 8, and the gravitational potential energy is 4 joule. At the lowest point, don't forget that, at the lowest point, the kinetic energy is 8 and the potential energy is 4. At the highest position of the swing, the kinetic energy and the gravitational potential energy are what? Now, let us imagine the situation. Now, try to draw your pendulum. This is the vertical position, which is the equilibrium position. The question claims that the kinetic energy here is 8 joules and the potential energy is 4 joules. Now, at the highest point, what is the meaning of the highest point? Highest point means no more velocity or speed. So the velocity at the highest point should be 0. Then the kinetic energy at the highest point, let us name it as top, equals 0. Now, here is the highest point. Let us name it as B, and the lowest point is A. Now, write down the conservation of kinetic energy, any formula. The one that will satisfy this question is kinetic energy at B plus potential energy at B, which is the final, equals kinetic energy at A plus the potential energy at A. Now let us substitute the situations. Kinetic energy at B, the highest point is 0, as we mentioned here, plus the potential energy at B, it is needed. The kinetic energy at A is 8 plus the potential energy at A is 4. 8 plus 4 is 12. So at B, at this point, kinetic energy is 0 and potential energy is 12 joules. Go back to the alternative. We have, what is the answer? I think it's C. Kinetic energy is 0 and the gravitational potential energy is 12. And you can generalize this procedure in any mechanical situation, not only for the pendulum, for any system with no resultant force acting on it, then the mechanical energy should be conserved, and we have kinetic plus potential energy at any point equal the kinetic and potential energy at any other point. Let's go to outcome number 4. Now, for this outcome, we need to apply the law of conservation of mechanical energy for isolated system. The meaning of isolated system is no external forces. I don't think so. Isolated system means no net force. No net force. With no dissipative forces involved to calculate different physical quantities. And the coverage sent by the ESE suggests that we need to discuss concept check 6.3 and concept check 6.4, page 170. Let's do it. First one, a spring with the spring constant K. Let us explain here what is the potential energy for the spring. Elastic potential energy is 1/2 K x squared, where is K is the spring constant and R is how much is the compression or expansion. So it is the change in the length. Change in the length. It may be compression or expansion. Now, a spring with a spring constant K is oriented vertically and compressed down a distance of x from its equilibrium position. An object of mass m is placed on the upper end of the spring, and the spring is released. The object rises a distance h, with h is much larger than x. This symbol is much larger, so you can ignore x comparing to h, above the equilibrium position of the spring. If the spring is then, now we have another situation. Let us draw the first situation. The first situation, that is, we have the spring here relaxing. So this is the original length of the spring. So let us name it as L0. Now, the question suggests that we compress the spring by x. So the length of the spring becomes like this. This distance is x. By putting an object of mass m on the spring here, we have an object of mass m. Then we release the object or the spring. The object will go with the spring up. At this point, the object will leave the spring and continue upward until it becomes at rest here. This is the highest point. You know what is the meaning of the highest point now, right? It is V equals 0. So the kinetic energy here is 0. The potential energy is the total mechanical energy, which is mgh. Now, by applying the conservation of mechanical energy here, you know that the kinetic energy at position, let us name it as A here, mechanical energy at A, it should be equals to the mechanical energy at B, which is the highest point. Here is B. Now, do your calculation. Kinetic energy at A plus potential energy at A plus the potential energy stored in the spring at A should be equal to kinetic energy at B plus potential energy at B, I mean the gravitational potential energy. At B we have no spring at B. The spring is down. So that's it. Now at A the mass is at rest, so the kinetic energy is 0. And if you consider this is the reference for measuring the potential energy, so the potential energy at A it should be also 0. We are left with only the potential energy by the spring, which is 1/2 kx squared, equals the kinetic energy at B, which is the highest point, is 0. We are left with the potential energy at B, which is mg times h plus x. Why we write such a thing? Because the question tells us that is the height above the equilibrium that reached by the object is h. So the total height from the reference point, which is at this line, is h plus x. But we know that we can ignore x with respect to hy, because the question tells us that h is much larger than x, so we can ignore x. Here we have 1/2 kx squared equals mg h. I will name it as h1, which is the first situation. The second situation starts from here. If the spring is then compressed downward by the same distance, and an object of mass 3m is placed on it, how high will the object rise when the spring is released? Comparing to the first situation, the question means comparing to the first situation. Now the second situation, we have the same spring with the same length. Then we compress it by the same distance, x, this is x, the same distance, and here is our reference plane, and here we have a new object which has a mass of 3m compared to the first one. The first one is m. Now let's apply the mechanical energy conservation as we did in the first situation. Now when we release the spring, this object will rise reaching the equilibrium, then it will disconnect from the spring and it will go up. I don't know where is it. Maybe here or here or here or here or here, anywhere. So let us draw it like this. This is the new h. Now this is h2. That one is h1. Now here we have A and here we have B. This is the highest point again for the second situation. Let us name it as C, distinguished from the first one. This is the situation C. Now the mechanical energy at A should be equal to the mechanical energy at C. At A we have kinetic energy at A plus gravitational potential energy at A plus elastic potential in the spring at A. The sum of these should be equal to the kinetic energy at C plus the potential energy, gravitational potential energy at C, and at C we have no spring. Now, again, at A we have rest, so there is no kinetic energy, and for the gravitational potential energy is 0 by considering the reference here. So we are left with only the elastic potential energy in the spring, which is 1/2 kx squared. This would be equal to the kinetic energy at C is 0 since it is the highest point. Now the potential energy, the gravitational potential energy at C, it is the mass, I make a capital letter for M here, G times H2 plus X. Now, what is the mass here? The mass in the second series, it is 3 mass than that, G H2. And again, we will assume that H2 is larger than, very large than X. So we can ignore X. On the left side, we have 1/2 kx squared. Now, comparing these two equations, the two left-sided are equal, so we are left with 3mgh2 equals mgh1. Why? Because the left side here is equal to the left side here, then the right sided should be equal. Now you can cancel m with m, g with g, and we are left with h2 equal 1/3 h1. So the answer should be 1/3 h1, which is C. This is a full and detailed answer, okay? It's easy, don't worry about it. But we solve it easily because x, we assume that is very small with respect to h1 and h2, so we can ignore it. Okay. Let's go to the, sorry, I forget that we have another question for the same outcome. For the same outcome, concept check 6.4, a ball of mass m is thrown vertically into the air with an initial speed of v. Which of the following equations correctly describe the maximum height h of the ball? It's a very easy question. Here is the initial position. We throw it up with a velocity of v upward or speed v. So the ball will go up, and as it go up, the speed will decreases. That means the kinetic energy is decreasing, and the potential energy will be increased until the ball comes to the highest point. We are now familiar with the highest point. Highest point means, yes, you are right, V equals 0. So the kinetic energy is 0. Let us name this situation 1, and this is B, the final. Now, the mechanical energy at the final position, which is B, equal the mechanical energy at the initial position, which is A. Now, substitute for the mechanical energy, kinetic energy at B plus potential energy at B equals kinetic energy at A plus potential energy, gravitational potential energy at A. Okay. Before we proceeding with this, we need to consider some reference frame, which is the lowest point. I prefer the lowest point to be the reference. What is the meaning of that? It means that the potential energy at this reference point or reference level reference level, the potential energy, gravitational potential energy should be 0. So we can cancel potential energy at A. Potential energy here is 0. Now for the highest point at B, we have no kinetic energy, as we mentioned before. Here, because B is the highest point. Now, what is the potential energy at B? It is mg times h equal the kinetic energy at A. It is 1/2 mv squared. We can cancel m with m. Then we need to make h as the subject of the law. Is v squared over 2g. That's it. Piece of cake. So the answer is E. Now we can go to the second outcome. And this outcome, the outcome is identify, read with me if you please, identify that kinetic energy is a scalar quantity and is always positive or equal to 0 if the object is at rest. Okay. And the suggested questions by the ESE coverage is question 7, 611 and 612. I wonder, because 611 and 612, they don't meet the outcome needed. 611 is about the friction, and 612 it is about something for enrichment. But I will discuss these two questions and I will discuss the outcome itself. So let's leave this now to discuss the outcome itself. Then I will go back to 611 and 612. Even 612 is not included in the material, or it is only for enrichment, but I will discuss it in case. So what is the kinetic energy? Since it is energy, so it is a scalar. It's obvious. Any energy is a scalar. But how we can discuss it in mathematical notation? The kinetic energy is 1/2 mv squared. M is a scalar. V itself, it is the velocity, so it is a vector. But v squared, it is like this, 1/2 mv as a vector dot v as a vector. This is a dot product. The dot product is a scalar. So scalar times scalar is scalar. So the kinetic energy is a scalar quantity. Now, v dot v, always it should be positive, since it is v squared. It is the square of the magnitude of a vector, so it is positive. So v dot v is positive. Suppose v is positive, dot positive, it is positive. Suppose v is negative, dot negative, it is positive. So v dot v is positive always. And the mass is positive as well. So the kinetic energy should be positive. Then the kinetic energy, always the kinetic energy for any object is larger than or equal to 0. It could not be less than 0. When the kinetic energy is 0, kinetic energy is 1/2 mv squared. no way the mass to be 0. So the mass is not equal 0. So then, to make the kinetic energy 0, the speed should be 0. So the object is at rest. So K equals 0 when the object is at rest. That's it. Now let us discuss these two questions which are not related to the object or the outcome as mentioned by the ESE coverage. Okay. For an object sliding on a ground, the friction force is always opposite to the direction of motion or the direction of displacement, because the friction is always opposite the motion. So the right answer is always acts in a direction opposite to the displacement or the motion or the velocity. All are the same. Now for the second question, and this should not be put in the exam as mentioned by the curriculum, but I will solve it. Some forces in nature vary with the inverse of the distance squared. That means F is proportional to 1 over x squared or r squared or something else. For force like this, how does the potential energy, which is U, vary with the distance? I think it is 6.4, section 6.4, which is for enrichment. Discuss this situation. The force is always can be delivered from the potential energy for conservative, like minus in one dimension du by dx. So du, it should be minus f dx. Always it is in one dimension. If you want u, you must integrate. U equals minus integration f dx. Now f, it is proportional to 1 over x squared. Like some constant c over x squared. So put it in the integration, minus integration c over x squared dx. This is minus integration c x to the power minus 2 dx. Minus c integration of x to the minus 2, it is x to minus 1 minus 2 plus 1 over minus 2 plus 1 plus some constant like k. Then we are left with minus this constant c, x to the power minus 1 over minus 1. Minus over minus 1, it would be positive, and x to the minus 1, it will go downward, so plus, don't forget the constant k, equals c over x. I cancel this minus 1 with this minus 1. X to the power minus 1 multiplied by x to the power 1 up and down. X to the power 1 with x to the power minus 1, it is 1. Then here we have x downward plus k. So u is proportional to 1 over x, the inverse of the displacement or the distance. So the correct answer is the potential energy varies with the inverse of the distance. It is C. This is our question. Now outcome number 6. So I emphasize again, the outcome is to identify the kinetic energy. This is the outcome, and this is our 2 questions which are not related to that outcome. In this outcome, we need to calculate the change in momentum due to the change in velocity as the difference between the final and the initial momenta. And the outcome suggests that we need to solve question 7.4 on page 215. This question will not satisfy this outcome again. It satisfies anything else. But I will solve this, and I will put now a question related to the outcome itself. Now 7.4, the value of the momentum for a system is the same at a later time as at an earlier time if there are no, it's obvious, no external forces acting on the object, because the particles or the system should be isolated. That means the net force, external force, is 0. Again, the expression external forces acting on the particle of the system is 0. It is have a problem. The net force should be 0. The net force should be 0, not no external force, because there may be external forces, but the net of them is 0. The resultant of them is 0. Now, you know that this is not calculation. The outcome suggests to calculate the change in the momentum. Now let us put some question here to satisfy the outcome. A ball is moving to the right with a speed of 5 meters per second. It collides with a vertical wall and reflected with a speed of 4 meters per second or 3 meters per second. If the mass of the object, which is ball, is 250 grams, find the change in its momentum. This is the wall, vertical wall, and the ball is approaching to the wall with a velocity of 5, and it collides with the ball and reflected with velocity of 3. What is the change in the momentum? First, mass is 250 gram, which is forbidden to use. Convert to kilogram, 250 times 10 to the minus 3 kilograms. It is 0.25 kilograms. Now, the change in the momentum is m times the change in the velocity, which is m v final minus v initial. Now, we must put here an arrows because it is a vector quantities. It's very important thing. Now, if you need only the magnitude, here I want magnitudes, only magnitudes. Delta B as a magnitude is mass times V final as a magnitude minus V initial as a magnitude. The mass is 0.25. V final is, go back to the draw, V final is a 3 to the left, so it should be written as minus 3 because it is to the left. Now we have another minus, but because of the expression, not for the direction. This minus is for the expression. V final minus V initial. V initial, it is 5, and it is to the right, so it is positive. This is a very important thing. When you try to find the momentum, don't forget to consider the direction well. Now, 0.25 times minus 3 minus 5, it is minus 8. So the answer should be minus 2, I think. And the unit is kilogram meter per second, or Newton times second. What is the meaning of this minus? That means away from the wall. Or to the left, or against the original direction. Now let's go to outcome number 7. I hope there is no problem with that as 5 and 6. In this outcome, we need to determine the instantaneous power by taking the dot product of the force vector and the object velocity vector. Now, what is the power in general? Power is W, which is the work over time, or energy over time. When we use this expression, we have to consider this as average power. And if you need to find it with the forces, it is V FV cosine theta. And this V is average. So all of these expressions is to find the power, the average power. But if you need instantaneous power, you cannot do W over T. You can make derivative, dW dt, or the derivative of energy with time. But if you need to find with the force, F times instantaneous velocity times cosine theta. In general, for machines, theta equals to 0 in general. What is the meaning of using, or why we use cosine theta? You know that F is a vector and V is a vector. And the multiplication here with cosine theta. So that means we have a dot product here. So the power equals force dot V. This is in dot notation. For calculation, F V cosine theta. If you use average velocity, then you will get average power. If you put instantaneous velocity, then you will have instantaneous power. Now let's go to these two questions for this outcome. While a boat is being towed at speed of 12 meter, this is V. The tension in the tow line is 6. We were here 6 what? Kilo. So we must multiply by 10 to the 3. 6 kilonewton. What is the power supplied to the boat through the tow line? It's very easy. B F V cosine theta. F is 6 times 10 to the 3 because it is kilonewton. V is 12. Cosine theta is 0 because the tow line is in the direction of the motion. Now make the calculation here. We have 6 times 12. It is 72 times 10 to the 3 watt. And you can convert it to kilowatt. And if you need it in hour, in horsepower, you can divide by 72 times 10 to the 3. You can divide it by 746, almost that, and it will be converted to horsepower. Because every 746 watt, equals to 1 horsepower. So the answer would be 96.5 horsepower. If the question needs that. Now the second question is, an engine expands 4 horsepower. Here, horsepower. Forget what is the horsepower. Again, let us put it in formal way. 1 horsepower equals 746 watt, or it is almost 3/4 of kilowatt. Now, an engine expends 40 horsepower. When I see horsepower, I name this number as a power. This is the power. Watt, power. Kilowatt, power. So any number with watt or kilowatt or horsepower is the power. So an engine expends 40 horsepower in moving a car along a level track at a speed of, this is V. Speed. How large the total force? We need the force acting on the car in the direction opposite to the motion of the car. Here we have a very important thing is the motion with constant speed. If you read the question, you will discover that it is constant speed or velocity. So we have here equilibrium situation. Then F net equals 0. And the acceleration is 0 as well. Why? Because V is constant. Then suppose the engine of the car apply this force F, then the opposite force is opposite to it. This is engine and this is the opposite force. Now F net equals F engine minus F opposite, which is equal to 0 since it's equilibrium. So F engine equals to F opposite to the motion. So if we find the force of the engine as a magnitude, we are at the force opposite, the same value for the opposite force on the motion. Now, to find the force of the engine, and we have the power, so don't worry, the law is very easy. F V cosine theta. Now, F equals to the power divided by V cosine theta, if we separate the variables. How much is the power? The power is 40 horsepower. That means 40 times 746. So the power is 40 times 746. We convert it to watt, into watt. The velocity is 15. Cosine, the engine, the force of the engine is with the motion, so the angle is 0. Cosine 0 is 1. Put these numbers in your calculator and you will get almost 1989 Newton. And if you use only 3 significant figures as suggested by the question, it will be rounded to 1990 Newton. So this is the engine of the force of the engine and the force opposite to the motion. They are the same and the same magnitude, but they are in different or opposite directions. The last question for this outcome is a car of mass. This is the mass. The symbol of the mass is m. Accelerates from rest, so V initial is 0. With a constant power output, this is the power. They insist in the horsepower, so I think they will bring it in the exam. They will consider it in the exam. So the power is 140.5 horsepower. Convert it into watt. It is 140.5 times 746 watt. Then the answer is 104,813, and it is in watt. If you use this number, don't round it, use it as it is, and then round at the last stage, okay? Or use the expression as it is. Neglecting air resistance, what is the speed of the car after? What is the meaning of after? It is the time. And he needs the speed, V final. V initial, V final, T. Oh, they are related in this relation. V final equals V initial plus A times T. That's it. How much V initial? It is 0. How much is acceleration? I don't know. How much is the time? The time is 4.55. Okay, so our problem is to find the acceleration. If you need to find the acceleration, go to Newton's second law. Emergency room, I name it ER. The force, we don't know. Oh, it's a big problem. We have the mass, but we don't have the force. Recall that the power is FV times cosine theta. Okay, so what is V? I need V. Okay, here we have a very critical situation. What is this V? Is it final or initial or what? Okay, don't worry. As we mentioned before, if you use average velocity, then B would be average. What is the average velocity here? The average velocity, if the acceleration is constant, is 1/2 V final minus V initial. We know that V initial is 0, so V average equal V final over 2. So we can put it here. V average equals F times V average, which is V final over 2. Cosine theta, it is 1, because it is in the same direction of the motion. What about if it is M times A? V final over 2. Then I have my M, my A. A, it should be equal from this double power over M V final. Put it back into here. V final equals V initial, which is 0, plus acceleration 2p over M V final times the time. I put it in here. Now we have V final here, multiplied by V final. Now you have V final squared equals 2b over V over M, and V will be cancelled, T. Then V final equals square root of 2b T over M. That's it. Now substitute your numbers. Oh, it's very hard question, teacher. Is there any way? Right, yes, there is any way. It's easier. And this is the one that I will show you now. Let us leave all of these and remember the last expression we have. V equals square root of 2bt over M. Do you remember that? Okay, let's go back and we will solve it again with another procedure easier than that. This is the answer. 2b square root 2bt over M. But I offer the first one to enlarge our thinking and to get some new ideas. The average power is delta E by delta T, as we mentioned earlier. For the average, we name that as work over T, E over T, FV cosine theta. Yeah, that's it. If you use omega delta over T or E over T, we mean average power. Fortunately, the power is constant as mentioned by the question. What is the meaning of constant power? Constant power, constant anything, means the average power equal the instantaneous one. It's a fact. When something is constant, so the average is equal to the same amount. So we have here power equals, here we have only kinetic energy, so delta kinetic energy over delta T. What is the delta kinetic energy? It is 1/2 M V final squared minus V initial squared over T. Now 1/2, it will become downward here, times T, M V final squared, and V initial squared is 0, equals to the power. Now make V as the subject of the law, so V squared final equals double pt over m, and that's it. V final equals square root 2pt over m. Now substitute your numbers. Square root of 2 times the power is 104,813. The time is 4.55 and the mass, I forget the mass, 942.4. 942.4. And the answer would be 31.8 meter per second. That's it. I hope you understand this. The second one, it's easier. Do it. Now let's go to the 8th outcome. By this outcome, we need to show that the work done on a particle by a force F when the particle undergoes displacement delta r is given by the scalar product of F dot delta r, which is F delta r cosine theta or alpha or any angle you want. First, let us discuss this question as suggested by the ESE coverage 5.11, then 5.30. Jack is holding a box that has a mass of m kilogram. He walks a distance of d meter at a constant speed of v. How much work in joules has Jack done on the box? We can solve this question by two procedures. First one is the work equals F dot delta R or F dot dr, alhamdulillah, which is F delta R cosine theta. Jack is holding the box. Obviously, he will hold it with a force upward, and he walk right or left. So this is D. The angle is 90. Cosine 90 is 0. Cosine 90 is 0, so the work is 0. That's it. Or we can go with W equals delta K. Delta K is 1/2 m V final squared minus V initial squared. But the question told us that he is moving with a constant speed. So V final equals V initial. So the square of V final equals the square of V initial. So they cancel each other and we have again 0. So the work is 0. So the answer for this question is 0. Now 5.30. You push your coach a distance of 4 meters. This is the distance across the living room floor with a horizontal force. This is your force. Let us name it as FA, applied force. The force of friction is Fk because it is kinetic friction. What is the work done by you? By the friction force, by the gravity, and by the net force. We have 4 questions, not 1. Now let us go with my work. Work by me is my force d cosine theta by me. This is the coach. This is my force. This is the friction. This is the gravity. And this is the motion. This is D. Now, what is the force of me? It is 200 times D 4 times cosine. The angle between my force and the distance is 0 since they are in the same direction. So the answer is 800 joules. Now the work by friction, WK I will name it, is FK, D the same D, cosine theta of the kinetic friction force equals, the friction force is 150 times the distance is 4 cosine the angle between the friction and the displacement is 180 because the displacement is to the right and the friction is to the left. They are opposite to each other, and we know that the opposite direction means the angle is 180. Cosine 180 is minus 1. 150 times 4, it is 600, times minus 1, it is minus 600 joules. Now, the work done by the gravity, let us name it as WG. It is the gravity force, D cosine theta for the gravity force. I will not find the FG. Leave it. You will know now, soon. And I will not substitute for D. I will substitute only for the angle. The angle between the force and the distance or the displacement is 90 degrees. This is the angle. Is 90 degrees. So cosine 90. And cosine 90, all of us know that the cosine 90 is 0. So the work done by the gravity in this situation is 0. Now we need the work done by the net force. W net equals W by me plus W by the friction plus W by the gravity. We have no other forces, me and friction and gravity. So add these works to each other. 800 plus minus 600 plus 0, it is 200 joules. And we can obtain the same answer by another way as here. W F net equals F net times D times the cosine for the F net. What are the net force for FA and FK and FG? FG we will not consider it because it is normal to the motion. So the net force now is only FA minus FK. FA it is 200 minus FK it is 150. So the answer is 50. Put it back in the formula here. F net is 50 times D is 4 cosine. The net force is positive, so it is with the motion. So cosine 0, cosine 0, 1. 50 times 4 it is 200 joule. This is another way to find the net work. So the net work may be found by adding individual works to each other or finding the work done by the net force itself. Now let's go to the ninth outcome. This outcome is apply the relationship between a particle kinetic energy, mass, and speed as kinetic energy equal 1/2 mv squared, measured in joules or Newton meter or kilogram meter squared over second squared. We discussed it earlier, I think, in second or which outcome? Let me check. With the first outcome. Okay. I don't know what is problem with the coverage. The coverage suggests to satisfy 9, outcome number 9, is to solve question 5.1, which is the same for the first outcome. Meanwhile, the outcome itself asks you to apply the relationship, not to find the unit of energy. What a pity. Okay. The answer is C, as we mentioned in outcome number 1. If you go back, you will find that because joule, Newton's time meter, in Newton it is kilogram meter per second squared times meter, so it is kilogram meter squared per second squared. Okay. But for this outcome itself, we need to apply this relation. Kinetic energy equals 1/2 mv squared. It's an easy expression to find the kinetic energy if you know the mass and the velocity. It's easy. Suppose the answer gives you a mass of 5 kilograms and velocity of maybe 8 meters per second. What is the kinetic energy? The kinetic energy is 1/2, m is 5, v it is 8, then squared. So the answer would be, yes, you are correct, 160 joule. That's it. Or this is some example, okay? Another example, the question may give you the kinetic energy. It is 180, suppose it is 180 joule, and the mass is 2. Find V. It's easy. K equals 1/2 mv squared. K it is 180. 1/2, the mass is 2 v squared. So if you solve this question, you will find the velocity as almost 13.4, something like that, meter per second. That's it. So don't worry about a question like this to find the kinetic energy, how to discover what is V if you know the kinetic energy and the mass, or what is mass if you know the kinetic energy and velocity. It's very easy questions. Now let's go to outcome number 10. I think it's an important question. Here we are asked to calculate graphically the work done on an object from an initial to final position using force versus position graph. Now, discuss the graph and the question. The graph shows the component F cosine theta of a net force that is acting on a 2 kilogram. 2 kilograms means the mass. 2 kilogram block as it moves along a flat horizontal surface. Find the net work done on the block. Then find the final speed of the block if it starts from rest. From rest, V initial equals 0. It's a very important question, especially the second one, because the second one includes the first one. For such a graph, if you have F versus X or F versus R, any distance, then the work equals the area under the graph. That's it. The only thing that you need to is at or how I need the work on which displacement. That's it. The question asked me to find the net work done on the block. So it's from start position here to the final one at 8. So I try to split the graph into something that I can calculate. Here we have, if you note that, we have two rectangles. This is the first one, the yellow one. This is a rectangle, and I can find its area. And then we have another rectangle from 5 to 7. This one. Now let's put the length and width of each rectangle. For the yellow one, the length is from 1 to 5, so the length is 5 minus 1, which is 4. And take a look to the unit. It is meter, so it's okay. It's okay. What is the width? The width is from here, which is 0, to 2. So the width is 2 minus 0, which is 2. Again, watch the unit. It is a Newton. It is not kilonewton or 10 to the power 2 Newton. It is a Newton. So it's okay. Now name this area as A1. Go to the green rectangle. The length is from 5 to 7, so it is 7 minus 5, which is 2. And the width is from 0 to minus 1. So the width is minus 1 minus 0, which is minus 1. Name this area as A2. A1 equals LW. L is 4 times W is 2, so it is 8 joules. Now for the second area, A2, also LW, L is 2 times W is minus 1 here for the green rectangle, so minus 2. Then the total area equals A1 plus A2. 8 plus minus 2, which is 6 joules. This is the first question, the network. Now, the network equals the total area needed, which is 6 joules. This is part A. Part B needs to find the speed. Now use energy work theorem or work kinetic energy theorem. Work kinetic energy theorem. What is this theorem? It states that work equals delta kinetic energy. Work equal the delta kinetic energy in 1/2 m V final squared minus V initial squared. The object starts from rest, so V initial squared. It starts from rest, so V initial is 0. Then multiplied by 2 over m to cancel 2 and m from V final. Then we have here 2 work over mass equals 2 will cancel with this 2 and m will cancel with this m. Then we are left with V final squared. So V final, the thing that we need is square root of 2W over mass. Square root of 2. The work is 6 as in part A, and the mass is how much is the mass? 2 kilograms. 2 kilograms over. So we have square root of 6. 2.45 almost meter per second. That's it. Now outcome number 11. This outcome is for recalling the unit of the power as watt, where watt is joule per second or kilogram meter squared per second cubed. The question suggested by the ESE is 5.5, page 150. I think this question will not come in this form. Why? Because it is direct question. Which of the following is the correct unit of the power? It is watt. No problem with that. I think the question will come from this side. How much is 1 watt? Now, the watt equals joule per second. Don't forget this, because power is energy or work per time. Energy or work, it is joule per time, it is second. So the watt is joule per second. What is the joule? The joule is a Newton meter, as we mentioned in the work, per second. Now, what is the Newton? Newton is, as we mentioned many times, kilogram meter per second times per second square, times meter over second. Now, kilogram meter second square second. So kilogram meter squared per second cube. Or you can put it like this, kilogram meter squared second to the power minus 3. I think that question will come in this form. Now outcome number 12. We will discuss it by 2 questions. Our outcome here needs to calculate the work done on an object by a spring force by integrating the force from the initial position to the final position of the object, or by using the known generic results of that integration. And the question suggests to satisfy this by 5.42 and 5.43 on page 151. 5.42, an ideal spring has a spring constant K equals 440 Newton per meter. It is very important to know what is the units. Calculate the distance. The spring must be stretched, so we need to calculate x. Why x? It is not L, because it is from its equilibrium position, so it is x, the extension or expansion. For 25 joule work to be done, the work done on the spring is 25 joules. Then now put the kinetic potential energy stored in the spring equals the work on that spring. The potential energy stored in the spring is 1/2 k x squared equals W. Multiply 2 sides by 2 over k. I think you are familiar with this procedure. X squared equals 2W over k. Then x equal square root 2W over k. The only thing you need now is to substitute square root 2. The work done is 25 over k. K is 4410 Newton per meter, and the answer would be almost 0.337. But regarding to the significant figures offered by the question, it should be two significant figures, so it is almost 0.34 according to the significant figures rule. Now let's go to the next questions. 5.43. For this question, a spring is stretched 5 centimeters. So this is x, and it is in centimeters, so it should be multiplied by 10 to the power minus 2 meter from its equilibrium position. If this stretching requires 30 joule of work, this is the work, and we discovered before it is the potential energy stored in the spring. What is the spring constant? It is the same, and I think they will bring this in the exam. US equals 1/2 k x squared. I need k, so keep k as a subject of the law. So you must multiply by 2 and divide by x squared to keep k alone. So you have 2u in the spring over x squared. 2 times u is in the spring, it is the same as the work, which is 30 joule. And x, it is 5 times 10 to the minus 2 in meter, then squared. So the answer should be 24,000, and the unit is Newton per meter. Or you can write it 24 kilonewton per meter. Very hard spring. Lucky him, or lucky it. Here we have this outcome. Apply the law of conservation of mechanical energy for an isolated system, no external force, no net force, with no dissipative forces involved, to calculate different physical quantity. And the coverage suggests question 6.41, page 184. A ball is thrown up in the air, reaching a height of 5 meters. Using energy conservation or consideration, determine its initial speed. It's a super easy question. We mentioned, or we discussed the situation before, but as a concept. Now here is the initial position, and we need to put this as a reference level. Means that the potential energy here is 0. Now we throw the ball upward, it will reach a highest point, and the meaning of highest point is V equals 0 and kinetic energy equals 0. Name the first point as A and the second as B. Now the mechanical energy at B equals the mechanical energy, sorry, at A. The mechanical energy is kinetic and potential for A and B. Now at A we have, by assumption, that the potential energy is 0, and at B we have for sure the kinetic energy is 0. So the potential energy at B, which is mgHb, equals the kinetic energy at A 1/2 mv at A squared. Now we can cancel m with m. Maybe you note that the mass is not matter for such questions. Any mass will satisfy the same conditions. Now we need to find the initial speed. Multiply by 2, 2g hb must be equal to va squared. So va equals square root of 2g hb, and that's it. Square root 2 times g 9.8 times hp, it is 5. So the answer is square root of, I think, 98. It is a 9.9, almost 9.90 meter per second square. Is plus or negative? Take the positive one because it is upward. Take the positive sign. Because it is upward. Throw upward. And that's it. You can solve it with the equation of motion. V final squared equals V initial squared plus 2A delta x. Change delta x into h and a into minus g. And we have here 2. V initial is 0 and we have V final squared. It is the same. Some people name this expression as conservation of mechanical energy law. Yes. Okay. Now let's go to outcome number 14. Now identify that collision can be either elastic, partially inelastic, or totally inelastic. Now for elastic collision, we must discuss this thing. For elastic collision, both kinetic energy and linear momentum are conserved. But for partially inelastic and totally inelastic, in these both two collisions, we have momentum is conserved kinetic energy is not conserved. What is the difference between partially inelastic and totally inelastic? Totally inelastic means particles become one object. They are merging with each other to make a new object. Partially inelastic the particles or object remains separated. Now go back to the question here. For totally elastic, they want to trick you by this. Totally elastic. It is elastic. Some students, when they hear totally, immediately say totally inelastic. No, totally elastic. Collision between two objects, which of the following statements is or are true? So because they put like this, maybe there is or there are more than one answer. The total mechanical energy is conserved. Yes, because it is totally elastic. The total kinetic energy is conserved. Yes, because it is elastic. The total momentum is conserved. Yes, because it is collision. The momentum of each object is conserved. No. The kinetic energy of each object is conserved. No. The momentum and the kinetic energy will be exchanged between objects. So the total is conserved, yes, but for individual, no. For the second question, 7.12, for totally inelastic. Now we have inelastic. Which one is or are true? Maybe there are more one correct answer. For totally inelastic, the total mechanical energy is conserved. No, there is some dissipation. The total kinetic energy is conserved. No. The total momentum is conserved. Yes, indeed, because it is a collision in isolated system. The total momentum after the collision is always zero. No. Not always zero. The total kinetic energy after the collision can never be zero. No. Because there is some motion after the collision. So the answer is C, only C. So 7.11, we have 3 correct answers. For 7.12, we have only 1 correct answer. Let's go now to outcome number 15. For this outcome, we have to calculate the linear momentum P of a particle as a product of particle's mass and velocity. So we need P as the product of the mass m and velocity v. Rank the following objects highest to lowest in terms of momentum and from highest to lowest in terms of energy. So we need to find the energy and the momentum for each case. First one, an asteroid with mass of 10 to the 6 kilogram and speed of 500. A. First we find the kinetic energy, then the momentum. Or first momentum, then the kinetic energy. The kinetic energy is 1/2 mv squared. The momentum is m times v. Or we can use for the momentum also this expression, if you remember, square root 2m times k. First, I will show you the first one, then I put the answer for the other as a practice for you. For the first one, the kinetic energy is 1/2. The mass is 10 to the power 6. The velocity is 500 meter per second, and we need to square it because it is v squared. And the answer would be 1.25 10 to the power 11 joules. For the momentum, m, it is 10 to the power 6 times the velocity is 500. So the answer is 5 10 to the 8. Or you can use this expression, square root 2 times m, which is 10 to the 6, times the kinetic energy, 1.25 10 to the 11. I think you will reach the same answer. Now the answer for the other branches are, so ranking the kinetic energy is, kinetic energy of A is larger than the kinetic energy of B, which is larger than the kinetic energy of D. Then we have here the kinetic energy of C, and at last the smallest one is the kinetic energy at situation A. Now for the potential, for the momentum, first we have a momentum of 10 to the power 8, which is for the first one. So the momentum of A is larger than the momentum at B, which is larger than the momentum at C, which is equal the momentum at D, and the last one, the least one, is the momentum of the situation A. Now for outcome number 16. Alhamdulillah, we are approaching to the end. Explain that the total energy, which is the sum of the all forms of energy, mechanical and other, is always conserved in an isolated system. It's obvious that if you add energy, so the energy you add it is your work. If you add to the energy, so the energy and your work are conserved. If you subtract some energy from the system, the work you done, which is negative, plus the energy is conserved. It's obvious. Now, we want to discuss it by two questions, 6.17 and 18 on page 183. An arrow is placed on a bow. The bowstring is pulled back and the arrow is shot straight up into the air. The arrow then comes back down and sticks into the ground. Describe all changes in work and energy that occurs. Now, first of all, you put the arrow on a bow and you pull back the arrow. Here, this is the bow and this is the string of the bow. Now, what you have to do, put the arrow here and you want to pull it back. something like this. So you do a work here by stretching it back. So here we have work, and this work is converted into elastic potential energy. Now if you aim your arrow upward, it will go up like this, like a projectile, and it will go back. Now at the beginning here, if we assume that the launch and the target at the same level, so here we have only kinetic energy, and the potential energy is 0. At the highest point, some students will say now the velocity is 0, so the kinetic energy is 0. No, it's surprised here, because we have a velocity here, which is the horizontal velocity, which will not change. So here we have kinetic energy and potential energy. But what is the special situation here? The potential energy is a maximum, and the kinetic energy is a minimum kinetic energy. Then the object will go back. At the end here, we have a 0 potential gravitational potential energy, and the kinetic energy is as the same as the beginning here. Name it Ka, here Kb, Ke, Kea equals Keb. Okay. Now, this is an interesting question. The identical billiard ball. Identical means the mass of the first one equals the mass of the second one. Mass of A equals mass of B equals M. Now, and two identical billiard balls starts means V initial for both is 0 at the same height and the same at the same time, and roll down different tracks as shown in the figure. Which of the ball has the highest speed at the end? It's a tricky question because there is no one highest than the other. Which one will get to the end first? So we have an answer for this. Let us discuss first the first one. For A. Consider this as a reference level. Then kinetic energy up plus potential energy up equals kinetic and potential down. So here the kinetic energy at A plus the potential energy at A equals the kinetic energy at C plus the potential energy at C. Okay. Where are our zeros? C, it is on the level, reference level. So the potential at C is 0. Alhamdulillah. تابنا وتابكم الله. And it starts from A, so kinetic energy at A is 0. Here we have UA 1/2 m dA squared equals at A we have potential, so mgHA equals 1/2 m b squared. Now cancel m with m, then you are left with b equals square root of 2gh. Now go back to the two tracks. The height of A is the same as the height of B. So V here, when the object is going down until it will reach here, V, I will name it as V1. And it would be constant because we have now horizontal with no friction. So it is here V1 and here V1 and here V2 and so on. Okay? V1, sorry. All of them are V1. But the situation is different for track B. Yes, it is the same height. So it will reach down with the same velocity. Okay, it's V1. And here V1. Now, at this portion, Alhamdulillah. At this portion, we have acceleration because the ball will go down more. So here we have acceleration. That means the velocity will be increased and it will become other velocity, name it as V2, where V2 is larger than V1. Now the object continues to reach here, then it will go up. Here we have deceleration. Which is opposite to the acceleration. Then the object will lose the gained velocity and come back to its initial velocity, which is V1. So both tracks, in both tracks, the object will leave with V1. But what happened to the time? Which time is less, or do they have the same? Time or what? I think you remember what we discussed here for object on track P. In this portion, the velocity of the first object at A, here, all the way here, it is V1. But for track B, the velocity between these two red line, is V2 because it is increased. So here, ball B will gain time. So it reaches the end faster. B reaches the end faster than A. Then it needs less time. So it will go out the track before A. Why? Because at this portion it increases the velocity, then it needs less time than track A, which have the velocity of V1, where V2 is larger than V1. I think it's easy and obvious. They will have the same velocity, yes, but B will be faster. How it come? The meaning of faster, yani less time. Why B needs less time? Because in the middle, its velocity increases rapidly, and it will continue in vertical position to come out from the other side. Okay, number 17. Now it is 3 at the morning, so apologize me if I am feel sleepy. Okay. For this outcome, we need to discuss question 6.9, page 182, to calculate the elastic potential energy of a block spring system. It's a super easy question. A spring has a spring constant, and we name the spring constant as K. How much potential energy you stored is in the spring when it is stretched 1 centimeter. This is X, and it should be multiplied by 10 to the minus 2 to become in meters. So US equals 1 half K X squared. 1 half K is, how much is K? 80. And X is 1 minus 1 to the power minus 2. And we have squared here. So the potential energy is 40 times 10 to the minus 4, 10 to the minus 3 joule, or 4 millijoules. And for now, number 18, solve problem related to the collision and impulse. Do you remember what is impulse? Impulse, it is F delta T or delta P or M delta V or V final minus V initial. That is the impulse. The question says that an 83 kilogram runner running back leaps straight ahead toward the end zone with a speed of 7.5. A 115 kilogram linebacker, keeping his feet on the ground, catches the running back and applies a force of 900 in the opposite direction, 4.75 seconds before the running back's feet touches the ground. What is the impulse? As we mentioned now, the impulse is, name it as J, F times delta T. I have F, which is 900, I think, and I have the time, 0.75 seconds. So 900 times 0.75, it is 675 Newton second. Now for the second one, what change in the running back's momentum does the impulse produce? Now I have the impulse, so I can find the velocity. Let's go back and put the number. The running back mass, this is M. For the running back, I will name it as 1. Leaps straight ahead toward the end zone with the speed of, this is the initial speed, V initial. 115 kilogram, this is the second mass, linebacker, keeping his feet on the ground, catches the running backs and apply a force is, this is the force, in the opposite direction, without mention in the opposite direction. It is in the opposite direction because they want to stop him. 4.75. Now I need to find what change in the running back momentum does the impulse. The change in the momentum is the impulse, and the impulse is 675 Newton per second. Okay, Some of you think that they have solved the question, which is wrong. Because F is minus 900, because it is opposite the direction. So the answer is minus 675. So delta B is minus 675 Newton per second. Now, if the question needs the velocity, it's easy. Because delta V, we have delta V, it is M delta V. M, we know M, which is M1. V final, we need to know it. Minus V initial. How much is V initial? I don't know. How can you find it? It is here. 6.5. I need V final. I have mass and I have delta V. So, super easy, I think. See, what is the running back's momentum when his feet touch the ground? Okay. See, I have delta B. Delta B equal B final minus B initial. That means B final equals delta B plus B initial. Now, how much is delta B? It is minus 675 plus B initial, put it here. B initial is M times V initial. How much is M? Is 83 times the velocity is 6.5, I think. 6.5. Okay. 6.5 times 83. It is 539.5 meter per second. Put it here. 539.5. Then make the addition. The answer would be minus 135.5 kilogram per second. If the linebacker keeps applying the same force after the runner jack's feet have touched the ground, is this still the only force acting to change the running back momentum? Is or not is? For D, we have other forces when he touched the ground, such as friction because he in motion, and the normal force. So we have friction when he touches the ground, and we have a normal force upward away from the surface. For outcome number 19, we need to relate impulse to the change in the momentum and to the average force acting on an object in a given time interval while two objects are in collision. Now, a driver is a golf club used to hit a golf ball a long distance. The head of the driver typically has a mass of 200. This is the mass of the club. Let us name it as M1. A skilled golfer can give the club head speed of, this is V1 initial. The mass of a golf ball, this is M2. The ball stay in contact with, so the ball of the golf has a velocity of 0. Always the initial velocity for the ball of the golf is 0. Then you hit it and it moves. The ball stay in contact with a time interval of 0.5. So delta T equals 0.5 watt millisecond. So 0.5 times 10 to the minus 3 seconds. So it is 5 10 to the minus 4 seconds. The problem of such question is you need to memorize these two expressions. It is very important to memorize them. And don't forget, for elastic, these are for elastic collision. From the question, it is noted that the collision is elastic. We have extra equation minus V1 final minus V2 final equals V1 initial minus V2 initial. The hidden formula. It means that relative velocity after collision equals the relative velocity before collision but in opposite direction. In the opposite direction. Okay? Now, if you memorize this equation, you can easily find the velocity of one particle to the other. Here we have information about the baseball, which is V1, and V2 is considered to be 0 because that is before collision. The ball of the golf is at rest. Now we can V1 initial, we have it, V2 initial is 0, so this is 0. Now if you need to find V final 2 for the ball, 2 is the ball, 1 is the driver, 2 is the ball. If you find V final 2 for the ball, V final, it is important to decide which is 1 and which is 2. V final 2 equals 2m1 over m1 plus m2 V1 initial. Substitute 2 times the mass is 45. Some of you will ask me 45 grams, should we convert it? Here we don't need to convert because it will be cancelled. Now M1 plus M2, M1 is 200 gram plus M2 45 grams. Now gram will cancel with the gram. You see? Multiply by V1 initial, it is 40. Now make the multiplication and everything else. 2 times 45 times 40 over 245. V final 2 is 14.7. It is important to decide which is the driver is 1 and the ball is 2. Now I need to find the speed of the ball after the collision. So I need to the ball is 2, V2 and the final. So I need to find V2 final. This is the last equation in front of you. It's 2 M1 over M1 plus M2 V1 final plus something. This something is 0. Why? Because it includes the velocity of the object 2, which is the ball at the beginning, initial, and the ball is at station, so it is at rest. So this is 0 plus 0. You know, this is 0. Now substitute 2. The mass of the driver is 0.2, 200 becomes 0.2 kilograms, and 45 becomes 0.045 kilograms. M1.2 plus M2.045 times V1 final, V1 initial. This is wrong. V1 initial. Here it is V1 initial, which is 40. If you make this calculation, you will get 65.3, I think, meter per second. Now try to find delta B for the ball. It is the mass of it, V final for it minus V initial for it. The mass of the ball is 0.045. V2 final is 65.3 minus 0. 0.045 times 65.3. It is 2.9385 Newton second. Now to find the force, F equals delta B over delta B, 2.9385 over the time interval is 0.5 times 10 to the minus 3, I think. 0.5 to the minus 3. The answer is 5877 in Newton, and that's it. It's a very important question. I think it will be in the paper questions. So you need to memorize these 4 equations, if you please, and the equation for the relative velocity. Alhamdulillah, we reached the final outcome. It is about applying the relationship between the average power and the work done on the power side. Okay. We discussed the power and work many times in this exam. Now here we have a 65 kilogram hiker. This is the mass M. Climbs to the second base camp on Nanga, something in Pakistan, at an altitude of 3,900 meters. Now it is the final altitude. then it is H final. Starting from, the meaning of from is the initial. From the first base at, this is H initial. The climb is made in 5 hours. This is the time. Time equals 5 hours. That is 5 times 60 minutes times 60 seconds. How it comes? How much is it? Please say 18,000 seconds. Okay. First, calculate the work done against the gravity. For A, I need the work against it. Find first the work of the gravity. It is minus delta U in the gravity, which is potential energy, gravitational potential energy, minus mg delta H minus mg H final, which is H2, minus H initial, which is Hi. Now substitute minus 65 times 9.8. H2, it is 3900. H1 is 2200. Substitute here 65 times 9.8 times 3900 minus 2200. It is 1082,900. What? Joule, sorry. Now consider the sign. This bracket is positive, and here we have a negative, so this is negative. Now work against gravity. Let's name it as WO equal minus W for the gravity, which is minus this amount 1082,900 joule without a minus. Now part B needs the average power. Okay, it's very easy. B average power equal work over time. I have the work 108,2900 over the time, it is 18,000. So the answer is 60.2 watt. Now for C, the question needs the rate of energy input required, assuming the energy conservation. So how much energy, if there is a 15% loss, that is the meaning of C. The rate of energy input required, assuming the energy conservation efficiency of the human body is 15. Here I have a comment on the phrase the rate. Should be the amount, not the rate. Except if they mean the power. Okay. If they want us to find the power, no problem. Because the rate of energy is the power. As in any question, if the question tells you find the rate of energy means power. So I need the power, but there is a loss of 15%. So, and the remaining is what I need, this one. So I will put it like this. 15% E equal the work needed above. So E equal that work over 15%. That work is 1082,900 over 15%, like this. So 1082,900 divided by 0.15. It is something like 7,219,333, and it is in now for part C, the rate of energy input required, assuming the energy conservation efficiency of the human body is 15%. My belief, the manual of the book is wrong here, because the manual of the book answer for the energy, and the question is for the rate of energy. Rate of energy means power. Rate of energy means power. Now there is a consumption of 15%, so this 60 is the rest. Now, so the 15% of the power needed equals the power that we discussed in chapter P, or question B. So the power needed times 15% equal the power reduced here in B. Now 15%, I can write it like this, 0.15. Power needed equals P, so P needed equals P over 0.15. P is 60.2 over 0.15, and the answer would be almost 401. I think this is the suitable solution for this question, for the rate of change. Rate of energy. But if you want to go to with the question, with the solution in the manual, they solve it like this: 0.15 E equals the work done. So E equals work done over 0.15. And they get something like 722, something like that, I think. Which is the same, we can take it from here. For 0, 1, this is the power needed. E needed is power times time, power needed. The power is 401 and the time needed is 18,000 seconds. So if you make this multiplication, you will get almost the same answer, 7220000. That is 7.22 times 10 to the 6 watt joule or megajoule. 7.22 megajoule. I wish you the very best and very good luck. Stay happy and well. Thank you. See you again in third semester, in which we will put some videos every day for the physics. Thank you.